In the prior two lessons, I just discussed the nature of bases and acids within water and what role water plays in the reaction. Now, also in those lessons, I mentioned the fact that most acid-base reactions in water are equilibrium reactions. Now, equilibrium reactions are reactions where the solution reaches a state of equilibrium. And that state of equilibrium is a state where certain species of molecules exist within the solution at certain concentrations. I talked about a strong base like sodium hydroxide, and I said the reaction goes virtually to completion. And it's not really much of an equilibrium at all. It lies far to the right. That is, when sodium hydroxide dissolves in water, you get almost 100% sodium ions and hydroxide ions based upon whatever you added. So if you added a mole, you'd get a mole. That is, if you added a mole of sodium hydroxide, you'd get a mole of sodium ions and a mole of hydroxide ions. If you don't like dealing with moles, let's just use some numbers. If you added 1,000,000 sodium hydroxide units, you would get 1,000,000 sodium ions and 1,000,000 hydroxide ions in solution, as long as you had enough water to actually dissolve it. But many, many, many acid-base reactions in water are equilibrium reactions. So if we take something like acetic acid, and I'm going to draw the carboxyl group on the acetic acid for clarity here, because I want to show the reactive hydrogen. This oxygen has two non-bonded pair on it. And this might look familiar. This bent bond here, this looks an awful lot like the water molecule. If you see that, well, you're right. It has much the same shape. And not only that, the electron density is highest at the oxygen and lowest at the hydrogen. So it's delta minus at the oxygen, delta positive at the hydrogen. If you react this with a base, and in this case our base is going to be water, the non-bonded pairs of the water molecule, that is the non-bonded pairs on the oxygen, can attack that hydrogen with our double-headed arrow, and those electrons will shift to the oxygen in the acetic acid. And we're going to use the equilibrium arrows here. This should have been completed to a, oops, that's right, CH2. Our product here is now O minus, and we have a carboxylate ion, and it's actually the acetate ion because we started with acetic acid, and our water has picked up that proton. So we have a negative charge on the acetate ion, and we have a positive charge on the hydronium ion, net charge on the right, 0, net charge on the left, 0, all good. So what do we have at equilibrium? Well, at equilibrium, this reaction hasn't gone to completion. That is, even though we added a certain amount of acetic acid, say we added 0.5 moles of acetic acid in 1 liter of water. When the reaction has been allowed to reach equilibrium, that is, it's all dissolved, it's been well mixed, and things are relatively unchanging. They're statically unchanging. Dynamically, the reaction is still going on. It's actually going forward and backwards at the same rate. We would find that at that equilibrium point, much of the 0.5 moles that we added is still in this protonated form. That is, it's still the acetic acid molecule. It's just a hydrated molecule. And a relatively small percentage, very low percent, 1 to 5%, somewhere in there, we could calculate the number exactly, is going to be in the form of this acetate ion. Well, you know from what you've learned so far in chemistry that the concentration of this hydronium ion in solution, sometimes your teacher refers to it just as H+. Other instructors will refer to it as H3O+. The concentration of this hydronium ion in solution determines the pH. In fact, it's the concentration of this relative to the concentration of hydroxide ion. But that determines the pH of the solution. If you produce very little of this, if the concentration is low at equilibrium, then the pH is not very low. So neutral solution, a neutral aqueous solution, has a pH of 7, and in acidic solutions we can drop all the way down to pH 0. And pH 0, very acidic, pH 7, neutral, anywhere in between is a range of acidity. So how acidic would this be? Well, we have ways of calculating that. And typically what we do is, for clarity's sake, is we use something called an ice table. But we also need to rely on skills that we learned when we took our lessons in equilibrium. And in our lessons in equilibrium, we learned about equilibrium constants. And this actually has a constant. It's called the Ka, the acid dissociation constant for this particular acid, that determines the concentration of hydronium ion that is formed at equilibrium time. In the next lesson, I'm going to review a little bit about equilibrium constants and the equilibrium expressions, constant expressions, and then using that equilibrium constant expression, we will look at a way to calculate the hydronium ion concentration at equilibrium. And Ka is a published number that we can look up for any given acid. So we'll look up the Ka for acetic acid and we'll do our calculations based on that.